Hello everybody, my name is Vedraj Shetty. I'm a data scientist at Blueprint Technologies. In this webinar, we're going to divide into three parts. In part one, I will give you an introduction to Azure Databricks. In part two, my colleague Kyung, who is also a data scientist at Blueprint Technologies, will speak on building machine learning pipelines. And in part three, I will return to speak on structured streaming. So let's talk about Azure Databricks. Azure Databricks is a fast, easy, and collaborative-based analytical platform and is very popular among data scientists and data engineers who find the whole process of building machine learning pipelines more productive, more secure, and highly scalable, and best of all, optimized for Azure. It integrates really well with many of Azure's popular products like the SQL Data Warehouse, Power BI, Active Directory, and Azure Storage. So let's go to our Azure account if you have one. If you don't have one, always feel free to open an account by Googling Azure Databricks and clicking on the Get Started button. Now, since I already have an Azure account and I'm subscribed to the Azure Database service, I'm going to go into Databricks Workspace and launch my notebook from here. So when I click on Launch Workspace, I will get to my Databricks account. So I sign in. Yeah, so you should be able to see this once you are signed into the Databricks account. Now, before you can actually start building a notebook, you need to first create a cluster. In order to create a cluster, you just click on clusters and then either choose one of the existing clusters, or if you want, you can create your own cluster by choosing the cluster type and also choosing which version of Spark you prefer, and any version of Python that you actually have preference over. And you can also choose the number of workers that you would prefer. So it goes from as low as to how many you want it over here. The best part is that if you enable auto scaling, you can save money as it runs very efficiently by automatically scaling based upon the workload. So once you created your cluster, it should be displayed in this list over here, or you can just use any of your existing clusters that are running, or you could restart a cluster that is actually not running yet. Now, for the purposes of this demo, I'm going to be using a dataset that I downloaded from seattle.gov, and that dataset is related to the salary of the government employees grouped by department and job titles. In order to use that dataset, I'm going to upload it in Azure Data Lake Store. To do that, first I'm going to go to connection error. Fix that. Okay, so I go to DB data, then I go to my folder I'm interested in and VS demo. So currently I have already uploaded that to my specific folder in ADLS, but you can do that by simply clicking on upload, clicking on the source of your data. In this case, it is going to be cityofseattle.gov. I say choose, and then I select add selected files. Since already I've done that process, I'm not going to add the duplicate file. So we have a file called City of Seattle wage data. And now we can start using this file in our notebook to do further analysis. So let's go to our Databricks account over here and select workspace. Click on our users, Shetty, and select my specific one. So in this case, it's going to be a notebook called Intro to Azure Databricks. Now let's read in the City of Seattle wage data file by calling in this particular cell called spark.read.csv. And I say header equals true because we know that in the first row of the data set contains the header information. So once I do that, I can see that. Actually, let me run this cell first. Okay, so let me run this cell. Let's confirm that it can be read. Okay, great. So you can see that it has run. And now I'm going to check the schema of the data frame. So currently the schema says that these the first four columns are of string type, and the hourly rate also is a string type. We know that the department, last name, and the first name, and job title can be of string type, but the hourly rate has a number on it. And currently, when I say when I ask Spark to infer the schema by default, it does it. It um, defaults it to string. Now let's change the schema for the hourly rate from string to float. We do that by calling this particular command over here, where we say salary data dot with column, and we name the column that we're interested in changing its uh, data type from string to float. And we do that by running this specific command over here. And we do that, and when we say print schema, there you go. You can see that the data type has changed from string to float for the hourly rate column. Now, if you want to just have a brief overview of what the data looks in salary data, it can be shown like this. Or if you want to see a graphical output, you can just click on this chart over here and say bar chart. There you go. So now very quickly, without having to use matplotlib, a library, or any other popular Python libraries for the purposes of plot. Okay, so we have utilized Databricks visualization tool to look very quickly at what is the average hourly rate. And the way we did that is by going to the plot options and clicking on the hourly rate as a value and the group by department. We can change the aggregation to anything that we want. So currently it was average, but we can change it to sum, or we can change it to the minimum. But in this case, let's stick to average for now. We can show the same thing by doing some very easy aggregations that are available in PySpark. So I say, okay, let me take the data frame. I group it by department, aggregate by the hourly rate. In this case, it's going to be average, and rename the column to something that is more suitable. In this case, it's going to be average underscore hourly underscore rate, and then order it in descending order. So what you see over here is the departments and your average salary and the average salary of the employees who work in the departments. So currently, the employees who work in the city auditor have the highest average hourly rate. Now let's say instead of the average salary, we want to know what is the maximum salary that is earned within each department. And we do that by almost copying this function over here, and instead of having average, we call it now max. And once we do that, we see that the city light now, there's someone in city light who earns a maximum salary of $166, and so on and so forth. Now let's say that we want to identify who that person is, that earns the highest salaries, and what are their job titles. We can do that by using the window function within PySpark. So the way we implement that is we call a window and we partition it by department, because we want to know within each department who earns the highest salary, and then we order it by the hourly rate. The reason we do this, we call order by hourly rate, is because this window function, when it processes through a data set, it will order it by department and then sort within each department who has the maximum salary. And so for example, in the case of city light, the rank equals 1 will be to that person who owns the highest salary, and rank equals 2 will be in the same department the person who owns the next highest salary. So what we're interested in is to filter out only those rows in which the rank equals 1 for every department, and that's why we call filter rank equals 1. If you want to know instead the person who has the next highest salary instead of the highest salary, we say rank equals 2. Now when we run this, we get a table which tells us within each department who what is their name and title, the person who earns the highest salary, and what their hourly rate is. And I created a new column called annual salary, which calculates their average salary simply by multiplying the hourly rate times the number of hours they work. I'm assuming it's 8 hours per day times 5 times 52. So we see that, in this way we can actually identify the entire row contents of that particular table, and not just like we saw earlier, where we can only get an aggregated view of the department and the maximum hourly rate within each department. But let's say now, instead of getting the highest salary details of within each department, we want to find out what is the lowest wage. So we simply do that by changing from descent to ascending order, and we change the order here as well from ascending equals false to ascending equals true. And when we run that, we see that there is somebody called Donald Felder who works at the Legislative City Council and who earns an hourly rate of 5.11, which seems extremely low because currently, if I'm not entirely wrong, was the minimum wage Washington comes to around $11 per hour. So either this data set is out of date, or there's a wrong value of hourly rate, or if he earns really less, if he earns really 5.11, then he's probably earning that is probably illegal. I don't know. Anyway, so what I have, or there could be an incorrect data entry, in which case it would be probably a good idea to check with the department and make sure that that person is not earning below the minimum national wage. Okay, so I had demonstrated to you how we could use Python-like statements to do data exploration analysis. But we can also extend this capability to people who come with other programming background. For example, the other three languages that are supported by Spark are R, SQL, and Scala, with Scala being given the first preference. Um, so let's say, for example, you are someone who does a lot of work in R, but because and now is looking to do some analysis using big data, but because of the limitations of running R within let's say within a laptop, you would find that you can do now the same analysis using much bigger data and a scalable fashion using in R. So the way to actually do that within a notebook is either you create a brand new notebook and choose the language option as R, or if you prefer to, you can also mix languages in the same notebook. So for example, in this specific notebook, I start off with Python, but now I'm going to demonstrate to you how you can use R and SQL. So the way you use R is simply by having the percentage sign before R and calling it, and that way you can start using pure native R commands. We start by importing the library called SparkR, and then we can read the same file that we read using Python, but calling read.df and saying header equals true. Let's inspect the data to make sure that it is being read correctly. And there you see, when we call head data, we can see that the data looks very similar to what we saw when we read using Python or PySpark. Let's do some very simple aggregation to demonstrate further that people who have experience in R can do exactly what they did in, say, for example, RStudio, and they can reuse their skills within PySpark or within Spark. So we aggregate the what we demonstrate here is we aggregate the data by department and find out the number of employees who were surveyed to get the average or to get the hourly rate. In this case, we see that the number of people who were surveyed in the police department was close to 2,000. So that demonstrates at a very basic level how someone with a skill in R can come to Spark and be able to utilize their existing skills to do in-depth analysis on big data. With the same analogy, anybody who comes with a very strong SQL background can continue to use their language skills to do big data analysis. But before we start being able to query the data in SQL, we need to first store the data in a temp view. We do that by calling the simple command here and say salary underscore data dot create temp view, and we call the temp view as salary data. Once we have that, just like we did with R, we need to identify within the cell that we expect to write SQL-like statements. We do that by calling %SQL, like in this case over here, right? And then just below it, we can write code like how you would normally write in a when you're doing SQL-like queries. So in this case, I want to select all the rows from the temporary view called salary data, but all the columns from the temporary view called salary data, but limit only to the first 10 rows. As you can see here, this looks exactly what we saw earlier. And now I want to do a very simple aggregation again in native SQL code, where I want to take each department and find out how many employees were surveyed within each department to get the salary related data. And when I do that, I can see that yes, with each department, the number of employees who were surveyed was approximately, in the case of the police department, was 2,000. So as you can see, you can, as long as you have any programming background in either of the 4 languages, which is Python or SQL or Scala, you can take advantage of the scalability features of Spark to do big data analysis. So this concludes part 1 of the webinar, and in part 2, Kyung, my colleague, will talk about building machine learning pipelines.
Hi, I'm Kyung Kim, Senior Data Scientist of Blueprint Technologies. In this webinar, I'm going to show you how to retrieve data from Azure Data Lake Storage, process them, and build a machine learning pipeline by using the Databricks platform. For this, I'm going to use one of the Kaggle dataset that is publicly available. The dataset was provided by a Chinese company, Talking Data, which is China's one of the largest big data platform service providers, covering over 70% of active mobile devices nationwide. Let's load the dataset, which was originally in the CVS file format, but I converted it to a Parquet file format. Using the read.parquet command, I can directly load the Parquet file from Azure Data Lake Storage. I ordered the dataset by columns, IP, and click time in ascending order. Let's look at the content of the dataset. By using the unique function of Databricks display, I can show the content of the data frame tr_raw. There are 8 columns in the dataset. The first is unique IP address, the second, the app IDs, the third, devices, and OS channel. And the click time is the time when the advertisement is clicked. Attributed time is the time when the ad is clicked and then the app is downloaded. When app is downloaded, is attributed becomes 1. In the dataset, the total number of the rows is 184 million. and the number of unique IPs is 277,000. Let's look at the click statistics. The first click occurred on November 6th, and the last click occurred on November 10th. That means during 3-day period, the data was collected. The click statistics can be shown by using display function. As you can see, number of clicks per small time window can be shown over a 3-day period. During the nighttime, the number of clicks is very low, but during daytime, clicks increase, and decrease during the nighttime, and increase, and so on. So there is a periodic patterns. Now, I will predict how likely the ads shown in mobile devices are going to be clicked and then downloaded. In other words, I will build a machine learning pipeline for predicting how likely the ads are going to be downloaded when the ads are clicked. I'm interested in predicting conversion rate. First step, I split the data into two. 70% of the data is going to be used as training, and 30% is going to be used as validation data set. After that, I'm going to apply a series of SQL transformers to transform data into different data frame. First one is a Unix time trans. This is select all row and convert click time into Unix time stamp. And then, using window function, I store a column that previous click time, and then subtract those two to compute time interval. After that, for each IP, I computed the total number of clicks per IP, and for the difference between first and last, the click time per IP, which is named as click time total interval, and also the mean click time interval, and the standard deviation of click time interval, and number of distinct app used, and number of distinct device used, OS channel used, and number of conversions, and finally the conversion rate, which is defined as conversions divided by total number of clicks. And using pipeline, we can describe this data engineering step into one. There are, in this case, 4 stages in transforming one data frame to another. And output is going to be TRIP, data frame, and input is TR training. Now let's look at the content of the data frame TRIP. There are a couple of interesting facts in here. There can be a lot of total number of clicks during 3-day time period. It can even like 20,000 clicks. So I believe this IP is from a generated bot. And click time total interval can also be quite different. Some IP is just like 1,244 seconds, but some IP is almost like 3 days. And click time interval mean can be like 254, but standard deviation can be even larger than mean time interval. So that means certain time period, the number of clicks are very frequently appear, but in certain time period, it's just seldomly, like rarely happens. And number of app counts can be even large, like 86, and device and OS counts and channel counts can be quite large. And also conversion can be large as well. So in this data set, what I would like to predict is conversion rate when features are given, such as from second column to the third last column. I'm not going to use convergence as a feature because convergence are directly related to conversion rate. So that's going to be too much information. And when the case that convergence are not known or not known previously, but we know the channel statistics and click statistics, and we would like to predict how many conversions or conversion rate is going to be. So that's our aim. We can display all these table contents, the contents of this table summarized in one plot. In here, x and y axis are different. Like it can be like conversion rate, click time interval, standard deviation, and so on. So for example, like this plot is total number of clicks versus conversion rate. When there are many clicks, conversion rate is very, very low. But with number of clicks are smaller than certain threshold value, then conversion rate can be very large. It would be better to screen out too many clicks because it leads us to a very low conversion rate. So when the click time total interval increases, there is a tendency that click time interval mean is also increased. And if you look at here, click time interval increases, the click time interval, like I said, the deviation also increase. And if you look at this data here, click time total interval can be like 1 day, 2 day, and 3 day. There are many data generated set by the duration of the data collected is going to be set by 1 day, 2 day, or 3 days. Especially these two seems like machine generated clicks because duration of the click is set by like a certain period of time, like 2 days and 3 days. Now let's move on to the machine learning training and prediction. First, I will define features to use. From the data frame TRIP, I choose my features as the second column to the third last column. Vector assembler transforms the feature columns to a single column of feature vectors. The input column is feature columns, and output column is features. Standard scaler transforms the feature vector column to a standardized form. Each feature is shifted and rescaled so that its new mean value equal to 0 and its new standard deviation equal to 1. The input is the output from the previous transformer, and the output of a standard scaler is the scaled features that will be used as input for the machine learning model. In our case, we are predicting conversion rate based on engineered features. Thus, machine learning problem becomes a regression problems. We will use random forest regressor, one of the widely used machine learning algorithms based on decision trees. The input variables for random forest regressor is scaled features, and its output is conversion rate. Now, the full machine learning pipeline can be constructed by including feature engineering pipeline that we constructed before, and assembler, scaler, and random forest estimator. By using training data set, we can train random forest regressor model, and the trained model can be saved onto the disk for model productionization. After training, I fed the test data set into the model to predict the conversion rate and compare the predicted values with the actual values. As the plot shows, the predicted values are quite similar to actual values. For example, this 400 value corresponds to 400. So actual value quite matches with prediction value. And R square value was computed to be 0.91, which is pretty good. Now, the entire machine learning pipeline can be constructed from various stages, such as Unix time transformation, previous time transformation, interval time transformation, feature transformation, assembler, scaler, and the random forest estimator. The input of the pipeline is raw data, and the output is conversion rate. In summary, in this webinar, I covered how to construct a machine learning pipeline, including data frame transformation, vectorization, standardization, and then random forest model training and prediction. All these machine learning stages can be saved and loaded for model productionization. This concludes the part 2. For the next part, Vedraj will talk about Spark streaming. Thank you.
Welcome back to part 3 of the webinar. My name is Vedraj Shetty. I work as a data scientist at Blueprint Technologies. Just as a recap of the last two parts of the webinar, in part 1, I introduced you to Azure Databricks and Spark. And in the part 2 of the webinar, Kyung talked about building machine learning pipelines within Azure Databricks using Spark. Now let's move on to part 3 of the webinar. Here I will be speaking to you about Spark streaming, more specifically structured streaming, and also mention some of the advantages and demonstrate to you the advantages that Spark streaming has over batch processing. So let's go to our notebook, which is present in the Azure Databricks. Conceptually, structured streaming treats all the data arriving as an unbounded input table, which means that each new item in the stream is like a row appended to the input table, and the results will be equivalent to having all of it and running as a batch job. The developer then defines a query on this input table as if it were a static table to compute a final result table that will be returned to an output sink. Spark automatically converts this batch-like query to a streaming execution plan. This is called incrementalization. Spark figures out what state needs to be maintained to update the result each time a record arrives. Finally, developers specify triggers, and this is important, to control when to update the results. Each time a trigger fires, Spark checks for new data, which is basically like new row in the input table, and incrementally updates the results. Since Apache Spark 2.0 was released, we have access to a new higher level streaming API, which will allow us to build structured streaming applications. I will also be demoing in this notebook how we can do some real-time filtering operation and move on to more complex streaming applications using machine learning pipeline to do some real-time predictions. Okay, let's start the notebook by checking to see if we have a Spark session automatically created when we create the notebook. Looks we have, and the Spark version is 2.2.1. Let's import some libraries that we are going to be needing over here. Now, in terms of the sample data, we are going to be using the same data that Kyung showed us in the previous webinar, and this is related to the trying to predict the ad click fraud. This is available for download in the Kaggle website. Currently, the file, which was originally in a CSV format, is now stored as a Parquet file. For those of you who are not familiar with the Parquet file format, it is basically it's a free and open source Apache. It's a free and open source column-oriented data store of the Apache Hadoop ecosystem. It's very efficient and is highly compressed, making reading and writing data extremely fast. So this data is currently sitting in the Azure Data Lake store, which is over here. If I just go back a few steps, so this is the UI for the Azure Data Lake store, And you can and if I go through fraud and if I see here, so yeah, this is the folder I'm interested in, which is a train sample parquet. And if I open here, I can see that this is a parquet file that's going to be read. Now this parquet file is contains only like 100,000 samples. Okay, so uh, let us start by reading in the data file, which is present in the train sample parquet folder. Once we have read in the data into the static data frame, let's have a look at what it actually contains. So it contains IP, app, device, and information on whether the app has been downloaded or not. An app has been downloaded if it is 1 and 0 in all the other cases. So let's start by doing some very simple batch processing, which is basically trying to filter the raw data and only retrieve that data where the app has been downloaded. So we're going to look at this filter condition where the is attributed is equal to 1. And we store it in the data frame called has downloaded. Now let's display what is actually present after the filtering operation has been completed. So as you can see, we have received a data frame called has downloaded where we only have information on those events where the user has downloaded the app. Let's complete the same transformation that we saw earlier under batch processing, but this time do it under a stream processing mode. So the way we are going to emulate the streaming process is by going to pretend that we are going to read one file at a time. So this is equivalent of like reading in streaming data where you're trying to read in a certain stream of data. So this stream of data is going to be in our case a specific file. Now this file is again going to be sourced from the Parquet as a Parquet file, which sits in the Azure Data Lake store. So because the Spark streaming can read in very large streams, we will not be able to use the sample data. So in this case, we will be using the Kaggle's original training sample, which contains nearly 200 million rows of worth of data. So just to give you an idea of what that looks like, so if I go to the folder where the file is sitting, and you can see here, yeah, so the streaming application is going to read each of these Parquet files one at a time to simulate a streaming condition. So let's define a schema for stream processing. Unlike a batch processing where we did not have to where we did not have to define the schema in advance, because in batch processing there's an option to infer the schema automatically. Unfortunately, for streaming purposes, we'll have to define the schema before we can start reading the data. So once we define the schema, then we can tell Spark to start reading the input data. And the only difference between streaming processing and batch processing is instead of having like read only, in case of batch, we have now read stream. We define the schema and also we tell Spark to emulate the streaming condition by reading one file at a time. We'll also be using the original data source over here, which contains nearly 200 million rows worth of data. And our streaming condition will be the same as in batch condition, where we'll be filtering only those data sources or those data points where the app has been downloaded. And to check and see if the streaming condition is actually being set, we will run the cell and make sure it is being done. Yes, it is showing us true. So the streaming, we are expecting the job to be run as a stream. Let the streaming begin. So what we're going to do here is once the data is being read and it's been filtered, we're going to write the output as a Parquet file in a Parquet file format in this specific location over here. And we start the streaming process and the filtering process by running this specific command in the cell. And once it's done, it's going to take some time to initialize the stream. And a few seconds, I'm going to show you the visualization. Oh, it's ready, where we can start to see the streaming process, where the data is being read one file at a time, is being processed, and is being dumped in a folder, which we will later retrieve to verify what we are expecting. So let's hang on to this part of the screen for a few more seconds. As you can see, that's 75,000 rows being read and processed around the same time, and before it is dumped in a output folder. So this is pretty cool visualization part from Databricks, and so this is actually happening in real time, and where as I said earlier, almost like 70,000 records are being read and processed before it's being dumped in a output folder, right? Let's stop this query because there are nearly like 200 million rows of data, and we don't want to. This can take a really long time, but for our demo purposes, I'm going to stop this now. And it has safely exited the streaming process. Now let's examine the output folder to make sure that we are reading the data. We are actually filtering the data based on a specific condition, which was like, has the app been downloaded? So let's read in the output data from the streaming application. And let's just read the first 10 records in that data. So what we're looking for is trying to make sure that we only get in this specific column all the rows in which the is attribute is equal to 1. As you can see here, we have been successfully able to stream in data and only download those data points where the app has been downloaded. So that's another part of the verification to make sure that yes, we are only being able to save those records where the app has been downloaded. We'll do a quick query. Um, and yep, as you can see, we only have data where the app has been downloaded. Now let's do some prediction streaming in real time. But before we jump into prediction streaming, let us revisit how we did machine learning in batch mode. I'd also like to talk about pipeline, a very useful feature in PySpark. So when we were, as Kyung had demonstrated in his machine learning part of the webinar, he had to go through certain steps of transformation, feature engineering, and finally building a machine learning model. Now, if I'm a member of a team who is not exactly interested in knowing what was the code that was used to develop the model and more interested in prediction, all I need to do is uh, reuse the pipeline that was saved during the machine learning process step. So I do that by calling the library pipeline model, and I load the pipeline which was saved during the previous machine learning step. So now I have the pipeline. Now this pipeline actually contains the steps and the stages that the data had gone through for the transformation and the feature engineering. And I'm also be able to use the pipeline model to do some future predictions on the data set. So I do that by simply calling pipeline.transform. Now this transform function, as I said earlier, goes to the same series of steps that was used to transform the data from a raw data to a processed data set, and it does an additional step of predicting the outcome of the new data set, and that is stored in a variable called predictions. Um, as we can see here, the conversion rate and the predicted conversion rate are almost linear. So, just to recall, the machine learning model was originally trying to predict the conversion rate given the input characteristics of a specific IP. Now let's do some real-time predictions via stream processing. Now I'm going to build here a brand new machine learning model which can predict if a user is going to download the app based on their input characteristics. So in order to do that, I am going to import some libraries and use a very specific machine learning algorithm called linear support vector classifiers. So here I import the raw data set and I filter out the bots. Now a bot is defined as those users who click on a lot of ads but never download the app. So once I'm able to filter them out, then I split the raw data into test and train sets. And then I do some very basic feature engineering. This feature engineering may not be useful in a real world for detection purposes, but for the purpose of this demo, it's more than sufficient. And then I build a machine learning model using the linear SVC function call. And I then build a pipeline which shows all the stages of the data processing and machine learning building process step. Now, because the model runs through nearly 150 million rows of data, it can take a really long time to train. Fortunately, I have run this model previously and I have saved it and persisted it to a disk. And now I am going to simply um, load the pipeline that was used to transform and build the machine learning model. So this is very similar to what I've shown you earlier. So once I have the pipeline is loaded, then I go to the next step of streaming the input data. So as we have seen earlier, I'm just going to call simply read stream from a particular source and the option of reading a maximum of 1 Parquet file at a time. So once I do that, I can see that it is being uh, connected to the data source, and then I tell the pipeline model to do the exact same transformations I had done during the training step. So this step takes care of that, and I check to see if it is being in a streaming mode. And as expected, it is true. Now this is the part which is the most interesting. So now I am going to take the input data, do all the transformations, and also do the part where I can predict in real time if a user is going to download the app or not. So say the write stream, I store it in memory for now, and then I'm going to start the streaming process. So this step will show us the predictions are being done in near real time. It's going to initialize, and yep, there you go. So what you see over here is almost 31,000 records are being streamed and they're being processed, and then the machine learning model is going through the data to predict if a user is going to download the app or not. So this is real-time prediction. So this is specifically useful in trying to detect frauds. And if you're having a real-time application that requires this process, then the Spark streaming makes it very easy to build machine learning models and which can predict in real time whether depending on your use case. In this particular case, we're trying to detect frauds. So let's stop this process in a clean way. So now we have the table stored in memory as a temp table called streaming predictions. We can store it for future purposes by persisting it to a disk. And this can be done either in the Databricks environment under a Hive table or in the Azure Databricks store as a Parquet file. And that can be done by calling this particular cell to store in a Hive table and this particular cell as a Parquet file. So this concludes this part of the presentation where we introduced the concept of Azure Databricks. We also showed you how we can do some machine learning within PySpark and how to do some structured streaming and prediction in real time. As you can see, it's very easy to run Spark jobs within Azure Databricks and in a secure and scalable manner. Thank you.